Hey, we're going to be looking at one of my favorite calculus proofs today. We're going to be looking at how we know that x to the n should differentiate to n times x to the n minus 1. It's a pretty cool proof. I've drawn a diagram so you can visualize what we're doing. We've got the gradient of the tangent to the curve at the point A. So this is what we're trying to find. We're trying to find the gradient of this tangent. But what we're going to do is, just like in first principles, we're going to take 2 points so that you can use the gradient formula connecting them. Now don't forget that both of these points now are on the line. The curve we're assuming is y equals to x to the n. So that means that we can rewrite the y coordinate. The first y coordinate would be x to the n, and the second coordinate where we've moved h distance along here, so imagine we've nudged along here by a distance of h, would be in fact x plus h to the power of m. We can put both of these into our gradient formula. So now we're finding the gradient that joins A to B. Okay, so we have y2 minus y1 on the top, and on the bottom we'll have x2 minus x1. Those two x's are going to cancel out and we're going to be left behind with h. The really cool thing about this proof is that you're going to use the binomial expansion here on x plus h to the m. That's the binomial expansion. We've already learned about that. So I'm going to show you. This will be our expression here for the binomial expansion of x plus h to the n. If you need a revision on the binomial expansion, especially when you have an unknown power, you can check out my playlist on that. So the pattern would go like follows. We would have n choose 0, n choose 1, all the way going down to n choose n for the coefficients. We would start on x to the power of n and decrease it by 1 each time until we end up at x to the power of 0. H is going the opposite way. You can think of there being a h to the 0 here, and it's increasing by 1 each time until it gets to h to the n. Okay, so a couple of reminders here that n choose 0 and n choose n are both 1. So we're going to know that this one would be 1 and this one would be 1. And another nice hint is that n choose 1 and n choose n minus 1, so this would be the second one and the second last one, are both equal to n, and we looked at the proof of those before. The two ones at the end, the first and the last, are going to be 1, and the second one and the second last are also going to be n. So I filled these in. Here I've got a dot 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 to represent all the terms that happen in between there. Now we know from our formula for gradient that we're subtracting x to the n. So what we're going to do is we're going to subtract this x to the n and this x to the n. Now we're going to divide by h. It's really important to note that the powers of h are increasing here. So if you remember, we thought about this one as like being h to the 0. This one's h to the 1. The next one will be h to 2, h to 3, all the way up to h to the m. When we divide by h, what we're going to be doing is we're going to be subtracting 1 from each power of h, because you can think the rules for indices say if I divide by h to the 1, for example, h cubed divided by h to the 1 would be h squared. So we're going to repeat this process by reducing each power of h by exactly 1. Okay, so imagine each one was divided by h. Now, the first expression where we did have a h to the 1 is independent of h. That's important. We're going to need that later. And the highest power of h is now h to the n minus 1. And this would start in being h to the 1, h to the 2, increasing all the way up to h to the n minus 1. Now we need to take the limit of our expression. We've already calculated that f of x plus h minus f of x divided by h is this expression here. If we take the values, or if we imagine that h is very, very, very close to 0, okay, that means that any powers of h would also be very, very close to 0. For example, if I multiplied a really, really, really small number powered, it would be pretty close to 0. So actually all of these are going to approximate or be pretty close to 0, leaving us only with this first term here. this term is independent of h, so it doesn't matter if h gets closer and closer to 0, it's going to stay the same. So we can say that the limit as h tends to 0 of f of x plus h minus f of x divided by h is n times x to the n minus 1. So if you had, for example, x cubed, you know that its derivative, or you know that the gradient of its tangent, it's going to be, if this is n, 3 times by x to the 3 minus 1, or it's going to be 3x squared, which is really pretty cool. It's the first calculus proof that I always teach that uses first principles. I hope you enjoyed that. I'm going to show you lots of practical examples of how you can do both proving things by first principles and how you can use this rule shortcut it in the upcoming series.